Hello and welcome to hypothesis testing in chapter 10 for statistics 1. So suppose we're looking at a company that runs an ad for the Super Bowl with the goal of increasing its brand name recognition in the general public to above 40%. Brand name recognition is the idea that when people see the name of the brand, they know what it means. So like if I say Tide, you're like detergent. You recognize it immediately and know what kind of products they sell, which is a good thing. So suppose they run the ad, and the day after the big game, 420 randomly chosen adults are polled to see if they know what the brand name is, and 181 of them recognize correctly that the company's product. So they were able to recognize the brand. Was the Super Bowl ad successful? So what you're really asking is, did it do a good enough job? Was it above 40%? So as you're looking at this, we have a claim about a population parameter. I want to see, is it bigger? Is it bigger than 40? So is p bigger than 0.4? And what I have is I have this sample information about this 181 people that said, yeah, I know what it is out of 420, which is a little bit bigger than 43%. I'm going to round a little bit here for the sake of space. So naive non-stats person is going to look at this and be like, oh, heck yeah. So 0.43, clearly that's bigger than 40. I'm convinced this is done. It's bigger. The ad was good and things happened. That was nice. But that's really not enough for a stats person because you know statistics, which means you know that just because something's bigger doesn't mean it's significantly bigger or has specific meaning beyond just random sampling error. You should look at 0.43 and ask yourself, is it different enough that it couldn't be caused by simple just sampling error? The fact that I grab a sample, you grab a sample, and we'll get different values. So you look at this, you want to know, is it bigger, is it unusually bigger or not? So you want to ask, is 0.43 unusual? Oh, that's terribly written compared to point 0.4. And the answer is, I know ways to do this. I know that the ways I can tell things are unusual are z-scores or perhaps using some probability. Because we know that z-scores that are bigger than 2 are pretty unusual, or bigger than 3 are very unusual, and that's our way of detecting whether or not something is significantly different. So we have a way of doing this. So you need to use those skills to attempt this. And how we're going to use this is a very formal system called doing a hypothesis test. So let's do one. So a report from the U.S. Product Safety Commission claims that at least 90%, let me move this menu a little. There we go. Oh, now you can see it in the recording. That's great. At least 90% of all American homes at least one smoke detector. The city fire department is running a public safety campaign about smoke detectors consisting of posters, billboards, and ads on the radio, TV, and newspaper. And the city wonders, is this effort raise the local level above the 90% national rate? The building inspector visits 400 randomly selected homes and finds that 376 of them have smoke detectors. Is this strong evidence that the local rate is actually higher? So the first thing we're going to form is what's called a null hypothesis. And we write that like the following, if it'll let me write. Oh, now I've got the thickest line ever. Oh, that's a thick O. All right. Woohoo. So a null hypothesis is a starting point. So the idea is that I have to have something to work with to be able to build a distribution and be able to build a sampling distribution. I've got to have something to start with. Null stands for zero, nothing, or start. It's a place to start at. So I'm going to start with assuming that, well, it's null. There's nothing going on. So the proportion is 90%. Yeah? So what I'm saying with my proportion here, my p, my little p, is I'm actually talking about the city's smoke detectors. I think it's the same as 90%. So remember, you want to think of nulls as statements as sameness or nothingness. Nothing going on. They're boring. They're zeros. Alternatively, you want to say, haha, I think there is something going on, or I have a plausible alternative of what I suspect might be happening that I'm researching and trying to decide if it's true or not. And that's that I think the actual proportion for the city is greater than the national average, or it's bigger than 90.90. And when you're looking at your ha, there's lots of ways these can turn out. This is a greater than specifically because we think, where is it based on they've actually, raised the local level above. There's those keywords telling that this is going to be a greater than. So I've got these two alternative options and ideas. I've got a place that I'm starting with, a null, and I've got a plausible alternative, and I want to see what does my evidence seem to support? What does my sample seem to show me? So let's look at our sample evidence, and we're going to think of this as evidence. So I got p hat is 376 out of 400. Sorry, I had to look at what the value was because I couldn't remember. Which is 0.94. And again, you might look at this and be like, oh, 0.94. That's significantly bigger. Well, be careful. It might be, it might not be. I need to actually do some digging and some investigating to see if it is or if it isn't. So what I want to do is I want to be able to use spread to see is it significantly different. So I'm going to scroll this up here. So what I want to do is I want to build a sampling distribution. So I've got this sample and I want to see where is it located. Is it really far from 90 or is it really close? So I'm going to use the HO to build the distribution. So we're going to start with the assumption, our starting place, our HO. I'm going to use that to figure out my standard deviation, which we know for proportions, that's really terrible, is the square root of PQ over N. It's the square root of 0.9, because that's my thing I'm assuming is my starting spot. 0.1, because that's 1 minus 0.9, and my sample size is 400. When you do that, you get 0.015. Usually these numbers are not that nice. That one's kind of pretty. And now I'm going to draw my distribution. I'm only going to draw it one direction because I don't need both directions. I just need to know where 0.9 lands. Or sorry, 0.94. So the center of this is going to be 0.9. And I'm going to go up one standard deviation, which is 0.915. So I'm just adding standard deviations to get these next ones. Add it again to get 0.93. Add it again to get 0.945. So that kind of gives me a locator. So looking back at my p hat, my 0.94 is probably like right here. There's p hat. So is it unusual compared to the center? Yeah, but I needed the spread to say that. So it's looking pretty unusual. Yeah. Let's look at finding the probability that I get that p hat, or something a little bit worse. So what I'm going to look at next is the probability that I get something that looks like my sample, which is 0.94, or bigger. And why bigger? Because that's my alternative. So that's where that greater than is coming from. It's like, I want to see and investigate, do I have something larger? Okay? So at this point, you pull out Minitab and you give it that mean standard deviation. This looks normal. So again, mean 0.9 based on our null. Our standard deviation 0.015. Tell it to do a right tail and give it the p-value of 0.945. And that's going to produce something very tiny. And rounding probably should have happened there. That's very unusual, very small p-value, very unlikely event, very improbable thing. So you should look at this and be like, I don't think that's very likely. And look at how this was built. We started assuming the null was what was going on. We used it to build the distribution. We looked at our probability using the null. And then that probability came out very unlikely with just one sample, not many, just one. So as you look at this, what it's saying is, oh yeah, if the null were what's going on, then it's very unlikely that we got that sample. That sample evidence doesn't seem to point towards the null. It looks like the alternative is more plausible. So what we're going to do is we're going to write a conclusion that states that. So what we want to say is that, and I actually think I'm going to type this one because I'm a little worried it's not going to fit otherwise. When I look at my alternative, it seems like that's the more plausible scenario. So what I'm going to say is that the evidence suggests that the city's ad campaign was successful in raising the proportion of homes with fire detectors. Oops, my spelling's going great. To being above the national average. Of 90%. So I'm saying it actually looks higher than what we've seen. So it was successful and it looks higher. So it's answering the question and saying specifically what it seems to be pointing at. Cool. Let's do some definitions. Because I did a bunch of stuff and didn't tell you what any of it is. Alright. Back to the pen. Or I guess I could type some of this. So Z, or the test statistic, is the Z-score that comes from your sample evidence. So it is just a Z-score. And it's just going to be Z, based on your null. I've got to write what your null looks like. Being that P is some P0 value. So this is just whatever value you put on the null hypothesis. So in the previous example, that was that 0.9. So how we found this was that was going to be our P hat value minus the one for our mean. So that's our P0 divided by the square root of P0 times Q0 over n. So notice you're always using the null to build this. And it acts like a z-score. So the larger it is, or the farther it is from 0, the more unusual it is. That's all. Alright, p-value. P-value I can do in words. So p-value, let's do red too, is the probability of getting the observed sample assuming that the null hypothesis was true, or is true rather. Now you have to be very careful with this. It's not saying that the null actually is true. It's this big assuming, like underline and hearts and stars and whatever you need to do to convince yourself that this is not what's going on. You don't have evidence that it's true or false at all. You're just going to use it to build your distribution. Assume that it's true and build your distribution and then find the probability. So the one we did just like that was we were like, hey, we're going to find the probability. Oh, is it going to let me do this? There it goes. That p hat is bigger than 0.9. And then we got a bunch of zeros. And then, oops, I missed my decimal point. And I have too many zeros, so we'll just pretend that's a 3. That looks like nothing. Yeah, we just did this. Okay, good enough. Okay, now for the more complicated one. The level of significance is something totally weird, and until I bring it up, it doesn't make a whole lot of sense. So, this is going to be cutoff value of when a sample P is significant evidence against the null hypothesis. I keep missing that one letter, just one letter and against. Can't do it all. So you can think of this as, when is my probability, my p-value, so small it's significant? The symbol we use for this is alpha, which I'm going to draw, and I'm going to write you a little table of what's going on here. So the symbol we use for this, oh come on pen, I would cut all the me complaining about pen moments, but I don't want to, is alpha. And the typical value used for alpha is 5%. So 0.05. This is our cutoff for when it's going to be small. So that means that if my p-value is less than alpha, I'm going to consider it small, and therefore I'm going to say, ooh, it doesn't look like that probability was very likely. This is evidence against my null hypothesis, so I'm going to reject the hoe. Oh yeah. Now, mathematicians are weird. We want to reject things. We want to say that it looks like the hoe is not what's going on. The fun thing about that is, remember, the hoes are boring. They're like nothing changed. There's nothing interesting going on. So rejecting it is a good thing. We want to say that yes, there's something interesting happening. There's a difference. There's something that's changed. So we want rejection because you should reject a hoe. But occasionally you'll have the opposite happen. You'll gather some evidence and it'll turn out that you end up with something that's really probable, like it happens 40% of the time. That's not good evidence against the null. In fact, that's more evidence that the null seems probable. But here's the thing that's kind of sad about that. When that happens, we do what's called a fail to reject. I said we want rejection. Hopefully that makes sense. The hoe. This is one of those cases where you look at what you've got, you look at your evidence, and you can't say that it's not that that's going on because it seems like it's possible that that would be the truth. Yikes. Notice we never actually declare it true. We just say what we have evidence for or against it. So what's interesting about this is it follows the American legal system almost exactly. When a person may or may not commit a crime, only they know if they are innocent or not. But they go before a jury and they are tried, assuming they are innocent, and then they look at the evidence and they declare you guilty or not guilty. They never declare you innocent, only you know if you are. This is sort of interesting because it's the same thing. We never declare a hoe true. We just say whether or not we're going to reject it. Weird, right? Okay, let's do another example. This one's slightly different. How about some candy again? So in a bag of M&Ms, 20% of the M&Ms are supposed to be orange. Suppose you open a bag and find that 21 of the 122 are orange. Does this contradict the company's claim? We're going to use 5% as our level of significance. So if we get our p-value and it's below 5%, we're going to reject. If it's above, we're going to fail to reject. Let's write our null and alternative. If you're following along, you might want to try practicing and going through and doing some of this without me to see how well you do. So maybe pause the video and try it on your own. I'm going to hop right into this. I like to do my alternative first because I think it's easier to spot because that's who I am as a person. Does this contradict? So what I'm looking for is something that's like greater than or less than or more or less, and I don't have any of that. So when that happens, what we do is we do what's called a two-tailed test. We say, I don't know if it's 20% or not, and I kind of don't care. I just want to know, is it different from what they claim? So different we do as a not equal to. And my null is just like the boring version of this. Nothing happened. It's 20%. It's the same as the company claims. Let's do our sample p. So that's going to be 21 out of 122. Which I'm going to round because I'm going to run out of space. But in general, not so much. Yeah, it's probably more decimal places than what you want. Ooh, 8. That's a pretty 8. Let's draw a picture and do our, oh my god, 2. Our sampling distribution for this one. So I need to come up with my standard deviation. And this one's going to be small. So SD, I'm going to save space, just write 1.7. But in my calculator, use more spaces than that. Remember, my sample size is 122. So this is approximately 0.034. And again, I'm rounding just to place this, so I know where it's at. So here's 0.20. Since this is below, I'm going to go down. So 0.20, just subtract 0.034, gets that first one. And already after that first standard deviation, I'm good because that's below 17. So I now know my sample is probably like right here, p hat, and that's pretty close to the mean. So this is probably not going to be good evidence. Let's see how bad it's going to be. Let's do our z statistic. So I'm going to take my sample evidence, 0.17, I'm going to round 2, and minus my hypothesized value 0.20, divide by my standard deviation. Minitab automatically does this calculation for you in case you were wondering. I didn't write this one down, so now I'm like pounding on my calculator furiously, trying to catch up. So that's going to be negative 0.82. Again, it's not even one whole standard deviation away from the mean, so it's not unusual at all. It's pretty close, actually. So it's not looking too interesting. So let's calculate our p-value. And this is where things is going to get a little weird. So I got to do the probability that my sample is less than negative 0.8235. And here's where I'm going to have to do something strange. Now, I chose less than, and you should be wondering why. And it's because, as you've noticed, I've always tried to move towards the more unusual. So if I were interested in what area this would be, I'm going to go towards the more unusual values or towards the tails. And this becomes problematic because I don't just have a less than up here in the alternative, I have a not equal to. So what we do is we use the fact that this is a symmetric distribution to grab what the other end should look like. So I'm actually going to grab this other tail. Now when you do that, so I'm essentially using the alternative to justify I need to double this to account for I need to have two tails, not just one. Hence the name of this being a two-tailed test. So I'll go ahead and calculate that probability on Minitab, which with all my rounding is very different from those of you who did this in class. And I have to double it, so I gotta multiply by times 2. 0.403. Oh boy, that's huge. That's very big. It's so big. That's such a big P. You know what I do with a big P? I don't reject it. So hopefully you're looking at this large value of P and you're like, oh, 0.403, that's way bigger than 0.05, my alpha level. So I'm going to look at this and say, ooh, fail to reject. Now I need to write a conclusion that goes with that. So I'm going to go back to typing again. Ooh, if it'll let me. That looks weird. Such a mixed mash grifting. Red. So I'm failing to reject my null hypothesis. So I'm going to say that the alternative hypothesis is the more plausible of the scenario. So I'm going to say, this is going to feel very weird for you. I can't say it's not 20%. Yeah? The evidence is insufficient to show that the company claim that the proportion of orange M and M's is 20%. So I can't say it's not that. My evidence seems to support the company's claim. So what I'm saying is insufficient evidence. I don't have enough evidence to say it's not that. In fact, it's kind of looking like what the company says. And that's as best as I could do. Yep. So we're going to do more of these in Minitab. And on Minitab they are much easier because this last calculation is super simple. You'll look at the z-score and the p-value and make your conclusion. The most important thing is going to be setting up good hypotheses.